And you've always got to look back at it if you need. All right, so properties of limits tell me I can take the limits of those two things separately. So I could think about this as the limit as x approaches infinity of 6 minus the limit as x approaches infinity of 3 over x squared. And what would the limit as x approaches infinity of 6 be? It's just 6 because there is no variable there. And no matter what you plug in, you just get 6 the whole time. It's a horizontal line at 6. So that just stays 6. And then for my limit as x approaches infinity of 3 over x squared, this is my pizza party problem. I've got 3 pizzas, and as the number of people who show up to my party goes to infinity, how much pizza do we get? 0, right? So that is going to be 0. So pretty much any time you have a number over a variable to a positive power, it could be any power. Like if it's square, it just gets to 0 quicker, right? It could be like, it can be a fractional power. It could be 1/2. It could be 0.1. It could be something like that. As long as it's positive, it's still eventually going to go to 0. So that gives me 6 minus 0, which is 6. Okay, this also, let's think about what the graph looks like for this. If I pull up Desmos here and I graph f of x equals 6 minus 3 over x squared, on the graph, it's your horizontal asymptote because you're talking about what happens way out at the end of the graph. So if I type in like y equals 6, you can see there, let me make that a dotted line. You can see right there, that is a horizontal asymptote for this graph. So as your numbers increase, this is going to like level out at 6. It looks like it touches, but if you zoom in, it's not actually touching there. So I don't think I really have any on our assignment or our notes that ask about a horizontal asymptote. But if you want to know the horizontal asymptote of a graph, you just need to do the limit as x approaches infinity and negative infinity. And it wouldn't change this. If it was negative infinity, we'd get the same answer for that. So on that problem, on your free response question where it asks for a horizontal asymptote, you're just going to do the limit as x approaches infinity of the function, and whatever you get for that answer is going to be your answer for your horizontal asymptote. It's going to be y equals that number for those. There. So, what happens when I have something like this? So I've got 2x minus 1 over x plus 1. In this case, do I have a number divided by another, like a variable? I do not. I have a variable in the denominator, but I also have one in the numerator. So it's like, here you're deciding that you're buying 2 times the number of people minus 1 pizzas, and then the number of people plus 1 show up, right? Like, both things are changing here. So it's not going to be as straightforward as just saying, 0 for this. So in this case, whenever we are doing this, we're going to look at how to do this. We're going to look at how to do this mathematically. And then I'm also going to give you a shortcut that you can use after we look at how to do it mathematically. There are a few times where like being able to do it mathematically is going to be required, like some special cases. So we need to know this way instead of just the shortcut. But you'll find once we are like doing the homework that you can use the shortcut on most things. So to find the limit of a rational function, rational means you got a fractional function with variables in the denominator. As x approaches infinity, divide each term by the highest degree variable from the denominator. And apply the properties of limits. So, in this case, in my denominator, I only have an x. Its degree is 1, but that is my highest degree. So what I'm going to do is I'm going to divide every single term by x. The 2 won't factor out of that top because you don't also have a 2 over here. And we can't just like change the negative here to a positive. That would, if they were both negative, like if I had something like negative 2x minus 2 over x plus 1, then negative 2 times x plus 1 over x plus 1 would work, and I could cancel, and I would get negative 2 for that. So like in that scenario, that would work, but it's not going to work in this case because I can't factor it out for those. So I'm going to have to divide everything by x, and that means what I'll be dealing with now is the limit as x approaches infinity of 2x over x. Well, the x's would just cancel. I'd have a 2 right there. Right here, I can't do anything with this. I get 1 over x. Right here, these cancel, but what do they cancel? What do they become when they cancel? 1, not 0. In this case, because x divided by x would be 1. And then the 1 over x right here, I really can't do anything with. Okay? So, properties of limits tell me that I can take the limit. Oh, yes, thank you. So properties of limits tell me I can take the limit of all these pieces separately. So I'm going to write this down. I never write this down when I'm actually doing the problems. I just think it in my head, but I want to be very clear about what's happening here for you guys. That means I'm doing the limit as x approaches infinity of 2 minus the limit as x approaches infinity of 1 over x over the limit as x approaches infinity of 1 minus the limit as x approaches infinity of 1 over x. Again, I never write that out, but that's what's happening in this next step. So as I do that limit as x approaches infinity of 2, what is that? It is 2. Right? It's just a constant, so you just get that number. What is the limit as x approaches infinity of 1 over x? 0, right? Because I've got a number divided by a variable. As that number in the bottom gets bigger and bigger and bigger, I've got 1/10, 100th, 1,000th. It goes to 0. Okay? In the bottom, I'll get a 1 right here for that first limit. And then we just did the same limit right here. You get a, I've changed that to a minus again. I just can't, it doesn't matter because we get a 0 here, but it could matter if it was different. So we get plus 0. And so that is going to give us just 2 as our answer for that. Okay, questions? Everybody okay here? All right, let's move on. Let's do a couple more examples of this. So, same strategy on this one. What is my highest degree variable from the denominator? The 5, the x to the 5th. So I'm going to divide everything by x to the 5th, top and bottom. It's a legal move because it's like multiplying the top and bottom by 1/5, 1 over x to the 5th. So as long as I'm doing it to the top and the bottom here and distributing it to every term, it's still equivalent to what we had before. So if I look at what this would give me, it's going to be the limit as x approaches infinity of, one of the x's can cancel here, so I'll have 3 over x to the 4th minus 1 over x to the 5th. And then here, the x to the 5th will cancel. I'll just get a 2. And then I'll have 5 over x to the 5th. And so what you're doing, I'm not going to write it this time, is you're taking the limit of each one of those little pieces separately, right? What is the limit as x approaches infinity of 3 over x to the 4th? That's going to be 0. We've got a number over a variable with a positive exponent. That's a 0. How about 1 over x to the 5th? Still 0. A number over a variable, positive exponent. That's going to be 0. How about the 2? 2. That is 2. It stays. And what about 5 over x to the 5th? 0. So I end up with 0 over 2. What is 0 divided by 2? 0. So 0 is my answer for that. Okay, we okay here? All right, let's look at one more before I impart some shortcut wisdom upon you. All right, you're taking highest degree variable from the denominator, not the numerator. What's your highest degree variable from the denominator? The x squared. It's got to be the denominator. If you do the numerator, it's technically equivalent, but it's not going to get you anywhere. You're going to get something that's undefined that you can't do anything with. So we're going to divide by x squared everywhere. And so we're going to have the limit as x approaches negative infinity of, right here, I'm going to have a 2x. Because those will cancel, but I don't have anything left in the denominator. Right here, I've just got to leave that 5 over x squared. Here, my x squareds cancel and I get a 3. And then I've got 1 over x squared. Okay, so when you do this, we're going to have something different happen on this problem, right? Because when I do the limit of each one of these pieces separately, this piece, and this piece are fine. We can figure those out. This one is a little more troublesome, right? Because I got to do the limit as x approaches negative infinity of 2x. You don't want to plug in infinity. That is like technically not correct to write down. You can kind of think in your mind of plugging in an infinity here. But for the sake of correct notation, let's do this. I'm going to do the limit as x approaches negative infinity of 2x. And I'm going to leave it there for a second, okay? What's the limit as x approaches? Actually, I'm going to write it out. Let me write it out long ways this time, just so we're really clear about what's happening. So we're doing limit as x approaches negative infinity of all of these things. And the difference in this problem doesn't have hardly anything to do with the fact that it's negative infinity. Because the limit as x approaches negative infinity of 5 over x squared is still what? 0. Alright, so I'm going to leave this alone for a second. Alright, what is the limit as x approaches negative infinity of 3? It is 3. And for limit as x approaches negative infinity of 1 over x squared? 0. Right there. Now let's just think. What is going to happen as I plug in bigger and bigger and bigger numbers right here? Negative infinity is what we're thinking about. You're not really plugging in negative infinity. That's impossible. But like 2 times negative 1,000. 2 times negative 1,000,000. 2 times negative a gazillion. What are you going to be approaching? It's going to be negative infinity, right? So like as you plug in bigger and bigger and bigger numbers, but they're negative because we're approaching negative infinity, you've got 2 times a really big negative number, which is going to give you a really, really big negative number, right? So this is going to approach negative infinity. Now, I'm going to write it down, but this is really the part that you're kind of like, let's do this. Let's put like a thinking bubble around this. You're really just kind of thinking this in your head. I know that on one of the problems I graded this summer, it said to ignore it. Like if they plug in negative infinity, which is technically not correct notation, but they get the right answer, ignore it and give them the points anyway. So it just depends on the rubric, on how that's going to be graded. So you could, like if you wrote this down, I don't think they're going to count it against you, but it's technically not correct to like plug in an infinity because it's not a real number. It's more of an idea. So, but if we're thinking about this, if I have negative infinity plus 0, what does it give me? Negative infinity. And then if I take that negative infinity and I divide it by 3, it's still negative infinity. So our answer for this would be negative infinity. They'd ignore it. As long as you have negative infinity as your answer. I think you would have to go all the way to negative infinity. Like if you left it negative infinity over 3, they'd be like, oh, she does not know that that's still negative infinity. So I cannot give this to her. So I think you'd have to have that final step. If you wrote these intermediate steps, you'd still be okay. Reese?
On something like number 2 of that part, can you plug in infinity there?
Is that the horizontal asymptote?
It's the f of x plus 2x e equals 2x, and you need to find the limit going to
Not quite.
and
Not quite. We got some E problems at the end of these notes that'll hopefully answer your question there. Sort of for the one where it's positive. Negatives are going to be different for this. So for regular rational equations, there's a shortcut for this that makes it so much faster, because if you were to flip ahead, I got like a bunch of limits here, and you're like, oh, it's going to take us forever, but it will not. Because notice here that we had a rational equation where we had x on top and x on bottom. My degree of my top was the same as my degree on the bottom, right? Now, if you think about like plugging numbers into this, if I have 2x minus 1 and x plus 1, as the numbers get bigger and bigger and bigger, that means I'm doing like 2 times 100 minus 1 over 100 plus 1, right? And then the next step, I'd be like maybe doing 2 times 1,000 minus 1 over 1,000 plus 1. Do the minus 1s and plus 1s matter much whenever you're plugging in numbers like 1,000 and 10,000 and a million? They're making very little difference, right? So if you only look at the highest variables, if they are the same, notice that our answer is just 2. The coefficient here was 1, so 2 divided by 1 gave us 2. Because all this stuff over here really doesn't matter all that much whenever you get to really, really, really big numbers. I always think of, there's like an old Eddie Murphy stand-up comedy thing, and he's talking about some really rich guy being married to a hairdresser. It's like, if you are a hairdresser and you marry somebody really rich, you're not going to still go to work every day and be like, oh, we got $60 million. Here's my extra 70 I made today. Now we got $60,070. Like, that's not, it doesn't matter that much, right? You got $60 million. Your 70 bucks that you made at the hair salon is not going to matter that much. It's kind of the same thing here. Like those ones with variables matter a lot because they get bigger and bigger and bigger. But the one is very, very small in comparison there. So if we have this scenario, we can shortcut our answer. Let's think of this scenario. I just have x to the first power right here. Oh gosh, I've just made things worse. That's supposed to be a first power. And then I have x to the fifth power on the bottom. So think about what's happening as you plug in big numbers. 3 times 100 minus 1 over 2 times 100 to the fifth power plus 5. in this case, what matters the most? That bottom part where it's being raised to the 5th power, right? This is huge. Is the 3 times 100? It is getting larger, but does it even matter much whenever you're raising something to the 5th power? For big numbers, it starts to not count. It is like whenever you compare, my salary to what Elon Musk has, right? Like, mine would not matter, would not change things if I, am there. So the highest exponent is what's going to matter. So if that highest exponent is in the bottom, what's getting bigger faster, the top or the bottom of this fraction? The bottom, right? The bottom is getting bigger faster because it has that highest exponent, so it's going to go to 0 every time for that. And if I have a bigger exponent on the top, you're going to have sort of the opposite happen here. The bigger exponent is on the top of the fraction is getting bigger and bigger and bigger faster. So it's either going to be positive or negative infinity. You do have to think about this a little bit. Because like in this case where we were approaching negative infinity, that meant our answer was negative infinity. Because that highest exponent right there was going to be a positive number times negative infinity, theoretically, which gave us negative infinity. If this was positive infinity right here, then we would get positive infinity for our answer. So you do have to think about those a little bit closer. But if you have a higher exponent in the top, you're either going to get positive infinity or negative infinity. Those are your only two possible answers. So I think did we do Bobo-Botno for horizontal asymptotes? So limits as x approaches infinity and negative infinity are how you find horizontal asymptotes. So Bobo-Botno works in this scenario. So it's technically written for horizontal asymptotes and not limits, but we can still, use them the same way. So Bobo is bigger on bottom, and then that O right there is a 0. So if your fraction has the bigger degree exponent on the bottom, then you're going to get 0 for your answer every time. Bigger on top, not 1. And so this is where it's technically written for horizontal asymptote. So if your rational equation has a bigger degree on top, there is not a horizontal asymptote. For what we mean, not 1 is going to be does not exist, which is going to be positive or negative infinity for us here. That limit is not going to exist because you're going to get positive or negative infinity. And then each DC is exponents are the same, divide coefficients. Okay, so when we do these problems, like your assignment tonight is going to have a lot of problems. It's probably like 15, 20 problems, which is a lot more than we normally have, because you can use this shortcut. They're not going to require you to show a lot of work. So if I look, for example, at example 5, what is the answer for example 5? It's going to be 0, because you got a bigger exponent on the bottom. Okay? Try the rest of these. There's a couple little twists that you might have to think about a little bit more, but try the rest of those. For 6, what do you guys think for that one? Okay, negative infinity? I don't think this one's negative infinity. It's positive. So, yeah, it's positive for this because, so this is where you may just kind of want to think about what's going on. Technically, it's not right to plug in infinities. But if we did, right, what's the only thing that really matters right here? It's that highest exponent, right? And it's in the top. So really, the only thing that really matters is this. And we know we're going to get infinity or negative infinity because we have the higher exponent in the numerator. This is really the only thing that matters once our numbers get really big. So if you think about doing negative infinity to the third, right? When I raise a negative infinity to the third power, is it positive or negative? It is still negative, right? Because negative infinity times negative, 3 negatives will still be negative. So I'm going to have negative times negative infinity, but because you've got that minus in front of it, you have negative times negative, which gives you positive infinity. So those are a little bit trickier to decide between the positive and negative infinity, but we should have definitely had it ruled down to those two on that one. Okay, 7's a little tricky. What do you guys think about 7? The question here becomes, what's the highest degree, right? Because here I just have x to the first power. Here I've got e to the x, which is not x to a power. It's not x to the third or x to the fourth or anything like that. But if you think about plugging numbers in to this, if I'm doing x to the first power, then 1 will be 1. 100 will be 100, right? 1,000 will be 1,000. It's just like that number just gets bigger in a linear sort of fashion, right? But if I'm thinking about e to the x, then I would have e to the first power. I'd have e to the 10th power, e to the 100th power. If we do, oh gosh, sorry, didn't do that. If we do e to the 100th power, where did my Desmos go? Right here. I don't even know if Desmos will do it. It might protest. I get 2.68 times 10 to the 43rd. That's scientific notation. It means I got to move this 43 places to the right. That gets bigger way faster, right? So a note right here is if you just have an e to the x, as long as x is approaching positive infinity, e to the x is greater than x to any power, right? So we consider it like it's got a bigger degree than any type of x to any power, even if it's x squared or x cubed or x to the 100th even. E to the x is bigger. So this one I would consider to be bigger on the bottom. I would get 0. There is going to be an exception that we're going to see coming soon if x approaches negative infinity. So we'll look at that in a minute. But if x is approaching positive infinity, e to the x is bigger. So that one's bigger on the bottom. Okay. Let's see. Kendall, what'd you get for number 8? What? 9. Perfect. Exponents are the same here. Just divide those coefficients. That x squared has a 1 in front of it. You'll get 9 for that one. All right, 9 and 10 are a little bit trickier because they are not multiplied out. Who can tell me what they got for number 9? What have you got? Connor? Yes, negative 1/3. Because it might look like this is bigger on the bottom because you have that x squared, but really this has to be multiplied out. So that numerator is really, if we double square, that numerator is really x squared minus 4x plus 4 right there. So we're looking at that -3 and the 1 right here. So we'll get negative 1/3 for that. So if you get something where it's not multiplied together, you have to at least think about it being multiplied together. You don't necessarily have to show the work for it, but you have to think of it that way. Which, looking at number 10, I should really probably change this problem because you could get this one right with the wrong reasoning for this one. For this, you could look for exponents being the same, and you could just look at like, oh, I got a 2x and a 5x, and I would divide those. But is that really what we're doing? We're thinking about what this looks like when it gets multiplied out, right? So you got a 2x squared. Does any of the rest of it really matter? Not really. I mean, if I did it, I would get plus 8x minus 3x minus 12. But do the 8x, 3x, or negative 12 matter? It's not the highest exponent, so it doesn't matter as x approaches infinity. And on the bottom, you would get 5x squared, and then technically you're getting plus x minus 15x minus 3, like that. That stuff doesn't really matter, so if you're doing this in your head, it's fine, and you would get 2/5 for this. So most of these you don't have to show work for, you're just thinking through them using that shortcut. Okay, questions? All right, there are some cases that we cannot do with the shortcut. Okay, so let's look at some cases that we cannot do with the shortcut. One example is when we have square roots. So if I look at this square root right here, I sort of have exponents are the same because I've just got x to the first power right here. And in the bottom, I've got an x squared, which is a higher exponent, but what am I doing to that x squared? Square rooting, which takes it back to x to the first power, right? So in this case, these problems are a little bit different because it does matter in these problems whether or not x approaches positive infinity or negative infinity. So if x approaches positive infinity, then the square root of x squared equals positive x. So I'm supposed to divide by the highest exponent from the denominator. But here it's all under the square root. So like if this whole thing is under the square root and I divide by x squared here and x squared here, which is what I need to do, in the top it's not under the square root. So what I have to do is I'm dividing by like the square root of x squared there, because whenever I divided by my x squared in the denominator, it was really underneath the square root. So if x is approaching infinity, the square root of x squared is just x. So I'm going to have the limit as x approaches infinity of, this is really just 3x over x minus 2 over x, and then I've got the square root of my x squareds cancel here. I just got 2 minus 1 over x squared. And really, if I want to here, these x's cancel also. So if I do the limit of each piece of this, limit of 3 is just 3. What is my limit as x approaches infinity of 2 over x? Number on top, we got 2 pizzas. We got infinity people coming to the party. 0 pizza for everybody, right? In the bottom, you got to keep your square root. Limit as x approaches infinity of 2 is just 2. What is our limit as x approaches infinity of 1 over x squared? 0. So this ends up being 3 over the square root of 2. You can leave it. It might be rationalized on a multiple choice problem, possibly. So there's a chance they do that and they take 3 over root 2 and they multiply by root 2 over root 2 and you get 3 root 2 over 2. There's a chance if it's multiple choice that's what they give you as the answer. But as far as like free response, you can leave it. You don't have to do anything there. Okay? So it's kind of divide coefficients here, a little. But the reason that I can't just tell you to treat that square root of x squared as the divide coefficients is because if x approaches negative infinity, things change. Okay? So, if x approaches negative infinity, then think about this. You're thinking of like the square root of negative 10 squared. You could think about that two ways. You could square it first and then take the root, in which case you would get a positive number. Or the square root and the square undo each other and you get negative 10, which is the way we need to think about it for this. So if I am plugging in a negative number right here and I'm having x approach negative infinity, the square root of x squared is going to be negative x, not positive x. For that. So this is the exact same problem that we had before. Our only exception is x is approaching negative infinity. We're going to do the exact same thing that we did before. This whole thing's underneath the square root. I'm dividing by x squared. I'm dividing by x squared. Right here, I'm dividing by the square root of x squared. Square root of x squared for this. But whenever I am having x approach negative infinity, the square root of x squared is actually a negative x. And so this is going to be minus 2 over negative x. And this will be, x squareds cancel here. This is still just the square root of 2. And then this is going to be 1 over x squared. It really only affects that stuff in the top because the stuff in the bottom is all under the square root and it's just going to simplify. So I'm going to write another step here and simplify just to be very clear about what's going on here. This is going to be negative 3 plus 2 over x. And I've got the square root of 2 minus 1 over x squared. And so now if I do the limit of each piece, limit of negative 3 is negative 3. The limit of 2 over x is 0 because I've got a number divided by x. Then I've got 2 minus 0, and that is going to give me negative 3 over the square root of 2. So as x approaches negative infinity, I get the opposite sign of what I got for the positive on that same problem. So square roots are something you want to watch out for. They're a little bit trickier. Maybe refer back to your notes whenever you see those. Okay, we got 2 more things that can be tricky. Any questions on this before we go on?
So if it's positive in the square root, it's just a regular number.
Right. It's just going to be like your square root of x squared just equals x, which is what we would normally think, but it switches if x approaches negative infinity, and we have to replace it with a negative x. Okay. All right. Let's skip this for the sake of time. I might come back to it, but we've only got 20 minutes left, and I want to make sure we get through everything and are able to talk about the free response a little bit, so I think we'll probably not have time for it. All right, let's talk about some trig. Okay, and I've left myself some space here because I want to prove something right here. Let's consider the limit as x approaches infinity of sine x over x. Now, we have already learned the limit as x approaches infinity. I'm sorry. We haven't learned that. Hold on, let me just get rid of that. We've already learned the limit as x approaches 0 of sine x over x. What is that? It is 1. This is not the same. X is approaching infinity here. So this is not 1. Okay? So don't get those mixed up. Whenever you're looking at these, it's really easy to get those mixed up if you're not paying attention to your details. So, to figure this out, I want to sort of write a proof for you here. So, when we were learning about trig and the unit circle, what was the highest value that sine could ever have? Like at the top of that unit circle, what's the highest value? 1. What about the bottom? -1. So would you guys agree that -1 is always less than or equal to sine of x, which is always less than or equal to +1? Sine of x always has to be between -1 and 1. Okay? So that is a true statement. We know that from the properties of trig that we have learned from the unit circle. So would it be mathematically correct if I divide this by x, divide this by x, and divide this by x? If I do it to everything, is it okay if I do that as long as I do it to everything? Should still be true. Okay? So this statement should still be true. Now, what we were concerned with is our limit as x approaches infinity. But if I try to do just direct substitution over here of sine x over x, I will get sine of infinity over infinity. Really, I'm not even supposed to do that. I'm not really supposed to plug in infinity. That's not really right, is it? But this is indeterminate form. We don't know. We don't know what that is there, so it's not helpful, right? That direct substitution doesn't do anything for us here. But what I have here is a squeeze theorem scenario, because I've got this function on the left that is always less than sine x over x. Well, what is the limit as x approaches infinity of -1 over x? What? 0, because I've got a number divided by a variable. We have -1 pizzas. Don't know how that's possible, but that's what we've got. We got infinity people at the party. Nobody gets any pizza, right? There. And then over here on the other side, I've got this, the limit as x approaches infinity of 1 over x. What is that? 0. So we could make a conclusion now. If I'm getting the same limits for these functions that are on either side here, we could say by the squeeze theorem, then it must be true that the limit as x approaches infinity of sine x over x also equals 0. So this is a fact that we can have memorized. To me, it's pretty easy to see why this is the case, because sine is always between -1 and 1. It's always a very small value, right? It goes back and forth, but it's always a very small value. So as the bottom of this fraction gets bigger and bigger and bigger, you've got something small over something bigger and bigger and bigger and bigger, and that's going to approach 0. And by similar reasoning, it would also be the same for cosine as well. Because cosine, we could just replace sine with cosine right here, and it would be the same proof. Cosine is also always between -infinity and infinity. So, these are really not all that bad to do right here. So if we look at this example, I've got sine of 3x over x. Sine of 3x, it really doesn't matter that I put the 3 in there. Sine is still between -1 and 1, right? So I got a little number over a number that's getting bigger and bigger and bigger and bigger and bigger. What am I going to get here? I'm just going to get 0 for that. So even with the 3 in there, you could even, if you want, you could think about like putting a 3 here and a 3 out here, but then you would just end up with 3 times 0, still 0, right, for that. 14's a little bit trickier because I got more things going on. Any ideas of what I could do here? Yep. Close. I think you said one thing wrong whenever you said that. I think you said 2x over 1, but it'd really be 2x over x. For that, you're dividing both there. Hello? Hey. Okay, we can't do that? Okay. 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 I'll ask Leslie. Okay. 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 All right. Yes, I will. I will. Okay. All right. Thank you, Michelle. All right, bye. So I'll split the pot tickets at the soccer game Friday. Buy one. Everybody comes to the soccer game on Friday. It's like our one chance at a Friday game. So, all right. So we can love connection this, where we divide right here and divide right here. That's what I would do. So that means you're doing the limit as x approaches infinity of 2x over x, and limit as x approaches infinity of cosine x over x. And here the x's just cancel. This is just 2. What is the limit as x approaches infinity of cosine x over x? Just 0. So we get 2 for the answer. Okay, questions? So just treat sine or cosine like it's 1. Technically it's not always 1, but if you just treat it like it's a 1, you'll get the right answer for those. Okay. All right, ease. And this comes into play on your free response question. We'll make sure we do that one also. Ease are a little bit different. Okay. So number 15 is a very simple, straightforward problem. It's not a fraction. And if you think about what would happen if you start plugging in bigger and bigger numbers for e to the x. If I plug in 1, I just get e to the first power. That's 2.71828, whatever it is. If I plug in 10, I get e to the 10th. If I plug in 100, I get e to the 100th. What's happening to that value of e to the x as it gets bigger and bigger and bigger and bigger? Getting closer to infinity. This is positive infinity. So, if you're not thinking much, you're going to think, oh, well, 16 is probably like still infinity or negative infinity, right? But your variable is where we're plugging in the negative infinity, right? So what I suggest for these, if you have ease, if you have any exponential where your variable is in the exponent, would it be equivalent if I do this, the limit as x approaches infinity of e to the negative x, right? So I just took, like, I'm going to be putting negative numbers up here. So instead of plugging in negative numbers, I'm going to put the negative up here, and I'm going to start plugging in positive numbers. Okay? This is equivalent. Like, if I want to do this on any problem, I could, but it really is only helpful on problems like these, where you have exponentials. So if I do that, e to the negative x, what do we do with those negative exponents so we don't have them anymore? They're like our bad children. We lock them in the basement. So limit as x approaches infinity of 1 over e to the x. And what is that going to be? I got 1 pizza. I got e to the infinity people coming to my party, which is infinity people, right? 0 for that. So the assignment that you have here is 1 through 6. We're going to look at the free response, so that's probably what you need to be getting out right now. The assignment is on page 115, or starts on page 115. It's 1 through 6. That is a matching. Those are matching problems where you have to match. Equations to a graph. Think about your limits for that. Like, think about your limit as x approaches infinity being that horizontal asymptote, and that'll help you on those. 13 through 37 odd is your homework. It is fine to use shortcuts on that. So if all you have written down is 13 is 2/3. Like, don't even copy the problem. That's fine. Because I don't want these to be ones that take you a really long time. It's way more problems than we usually do because you should be able to do them quickly. Let's look at the free response, because we need to look at specifically these problems. Here they are. Normally, I let you guys choose which ones you need to look at. Considering that we've only got 7 minutes and you only just now learned how to do 1B and 2. Let's do those this time. So, I have got the function f of x equals 2x e to the 2x. So, the limit as x approaches infinity of 2x e to the 2x. If I'm thinking of plugging in positive infinity, I'm not going to write it down because that's technically wrong. I am doing 2 times a really big positive number, e to the 2 times a really big positive number. Everything involved there are really big positive numbers, right? So what am I going to get for that? I'm just going to get positive infinity for that. You don't have to show work. We're going over it right now. Memorize it in case it shows up for tomorrow. That's fine. No, you don't have to show any work for that. So that is just going to be infinity. As you plug in bigger and bigger numbers, that just gets bigger and bigger and bigger. But if I'm doing the limit as x approaches negative infinity of 2x e to the 2x. This is that scenario like that last example. I'm doing negative infinity to an exponent, which is going to cause me problems. So instead, the work that you can show on this is rewrite it. Limit as x approaches infinity. I'm going to make it a positive infinity problem, which means I need to make both of my x's negative. Well, technically it's 2 times negative x right there. So this is still equivalent to what I had. So if I simplify this further, that is the 2 and the negative x is just going to be negative 2x. And I'm going to write this as e to the negative 2x. And when I have a negative exponent, I can treat my negative exponents like my bad children, right? I'm going to take the base and all this, I'm going to lock it in the basement. It's an effective child rearing strategy. It makes the exponent positive. So this is going to be negative 2x over e to the positive 2x. So now I'm thinking Bobo Botno eats DC. Is this one bigger on top, bigger on bottom, or exponents are the same? It's a tricky bigger on bottom situation. E's, even if it's a 2x, are bigger than any x at any power right here. So this one is bigger on bottom. You just get 0 for that. Okay, does that make sense? All right, let's look back at the horizontal asymptote part of 1B. No, 1C. So vertical asymptotes, you're just looking where the denominator equals 0 but does not cancel out. Horizontal asymptotes, it has a hint right there, limit notation. You don't necessarily have to put the limits for the vertical. I think I may have put them on my key, but I can live without those. But for the horizontal asymptote, right here, to find the horizontal asymptote for this function, it's just a regular rational function. You're going to do the limit as x approaches infinity of, what do we have? 2x minus 2 over x squared plus x minus 2. Okay? You don't have to show any work or reasoning here. Bobo bot no eats CC. Also, don't write down Bobo bot no eats CC. That is not official math language there. But Bobo bot no eats CC. What have we got here? Bigger on bottom. That is 0. Now, you do need to write that there is a horizontal asymptote at, you need to give the equation for the horizontal asymptote because it says write an equation. So that is y equals 0. That's a horizontal line, y equals 0 for that. Your vertical asymptotes here where you cancel, that should already be up there. Okay. Everybody okay there? Like this is enough work right here. That would get you full credit. For the horizontal asymptote, it also needs the vertical because it asks for that. Vertical, really, you're just going to factor it. So it's like 2 times x minus 1 over x, and you can pack up as I'm showing you this, x plus 2, x minus 1, and we're just going to cancel those. So you have a hole at x equals 1. It didn't ask you about that. You would say that there's a vertical asymptote at x equals, why'd I quit writing, x equals negative 2. So like that would be sufficient evidence for me here. I can live without limit notation on the verticals, but the horizontal you definitely have to have it. All right.